These are the notes for LT2 in the space science unit, and Target says that you can predict how the gravitational force between an object changes when the distance between them changes, and then we'll also deal a little bit with a mass change, but that will be more Target 3. Right now we're primarily concerned about what happens between the force of gravity and two objects when they get either closer together or farther apart. Now, you can see a picture right here, and if you're not in class, hopefully you can find a way to get this picture from me, or do the best you can and sketch it here in your notebook. All right, but if you were in class, you know we just glue these in. And before we even talk about gravity, let's look at this picture. All right, what this says is if you have a light bulb, think about a flashlight, and you've got somebody really close to you and you shine it in their eyes. We know that that light doesn't have a long time to spread out, so it stays very concentrated, and it only takes up 1 unit of space. So let's say that this is 1 unit of distance. Now, instead of shining it in a person's eye like right next to you, let's say there's somebody twice as far away. Look how quickly this light spreads out. All of a sudden, it takes up 4 units of distance, but we're really only 1 unit farther. Okay, so in total, though, we have doubled the distance. Well, let's go out another unit farther. So there's somebody, maybe if this is 1 meter, then there's somebody 2 meters away. And now there's somebody 3 meters away. We know that the light is not going to be as intense, it's not going to be as bright, and it's going to cover more area. Okay, 3 times farther away, it's 9 times less intense, takes up 9 times more space. So up here, it talks about the intensity of light. So that's a 1, a unit of 1 for intensity. So we've got going up here. 1/4 is intense. 1/9 is intense. Imagine if we went out 4 units. Well, you might be seeing a pattern here. 1 squared is 1. 2 squared, right, because they're out twice as far as 4. 3 squared, 9. 4 squared, we would have 16 squares, and it'd be 1/16 as bright. This inverse square law is actually considered a unified theory, so it relates a lot of things. It isn't just light that behaves this way. It isn't just gravity. It isn't just electrical forces, all right? So there's a lot of things that follow this pattern, and that's why this is such a big deal. There's a video on Moodle you should watch, all right, that we watch in class that talks about this inverse square law. And we're going to put just a couple things in the notebook, because for the most part, this is just going to be practice problems. So the inverse square law, the formula relates intensity of something. And obviously, since it is space science, the intensity we're going to be concerned most about is gravity. So the intensity of something to its distance. It's the inverse square law. And we know in math class, the inverse of something would have a 1 in the numerator. It's going to be 1 over d squared. This d that we refer to is going to be the separation distance. The separation distance. So we got a distance of 1 away. Here it was 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. All right. We're going to apply it to one more thing that's not gravity before we get into the kind of the possibly a little bit more difficult stuff. Sorry about that. And let's look at something most of us has probably done. Let's say you're spray painting. Okay, maybe you've got a can, maybe you've got like one of the professional commercial paint sprayers. And by now in the course, you know how fantastic my drawings are. So here's a person, that is a really big spray paint can. So there's this little spray paint can, he, she, whatever. All right, there we go. And let's say that you get really close to the object you're spraying. And then we're just going to get further away. Further away. All right. So let's say the distance is 1 meter. If we wanted to measure the intensity, so how thick that paint goes on, 1 is part of the formula. All right, so I probably should refer to this. On your formula sheet, inverse square law, it's exactly like we have in our notes. Okay, ignore this. Intensity is 1 divided by distance squared, just so you know where it is. So 1 divided by this 1 meter squared. So it's 1 divided by 1, because 1 squared is 1. So it goes on 1 unit thick. Okay? And it's going to cover a small space. If we back it out a little bit, let's say now we're at 2 meters total. Well, intensity is 1 over 2 squared. 2 times 2 is 4. So 1/4 is the intensity. So it's 1/4 as thick, but think about the space it covers up. It's going to have an area 4 times as large. So 4 times thinner layer of paint, but covers a 4 times bigger area. Let's go out 3 meters. Hopefully you're seeing the pattern. 1 over 3 squared. 3 times 3 is 9. So the intensity now, it's 1/9 as thick as if you were 1 meter away. But you're going to cover with that spray paint 9 times the area. And we could go out, it doesn't matter, we could go out 5 times farther. Think about that. Well, 5 squared is 25. We'd have 25 squares of area that we're covering, and it would be 1 over 5 squared, so 1/25 is thick. All right, so that's the idea, is that as you get farther away from the source of something, whether it's light, whether it's a planet's gravitational pull, whether it's a spray paint can, okay, the intensity goes down, but the amount of space that is covered by this force or this paint or this light goes up. All right, so that gets us to the next part. These practice problems. They should be on Moodle. Also, though, hopefully you are possibly able to get it from me in class, because I can't zoom in when I do this type of recording. It is what it is, so to speak. So I'll try to read this for you. But this is going to be where you want to write some steps down. Okay, so you want to pause me and get out your formula sheet if you have not. All right, it's a 3-step process, and the first step in these types of problems is to compare your distances. So problem 1 says, if the gravitational force between 2 objects that are 15 meters apart is 100 newtons, what would be the force between the objects if now they're 45 meters? So in other words, you start out at 15, you end at 45. First step, compare your distances. You can always do the larger divided by the smaller. It won't matter. Okay, so 45 divided by 15 is 3. Okay, that's your first step. Your second step, once you figure out how much closer or farther away are we getting, is you square that answer, because it's the square law is part of it. 3 caret 2, so 3 squared is 9. Now the third step, not as easy to put into words necessarily, but if in the problem you're getting farther apart, so these 2 objects started 15 meters apart, now they are 45 meters, we know that as things get farther away, the force between them gets weaker. The intensity of the light gets weaker, okay, whatever the case might be. So if we started out with 100 newtons of force between these 2 objects, and we're getting 9 times weaker, we go 100 divided by 9. If we had flipped it, if we had started 45 meters apart and actually got closer, then we would have multiplied by 9. When you get that, it's like 11.1 repeating, and we know that in Moodle we usually round to the 10th. So 11.1 newtons would be the new force. All right, so on our formula sheet, compare your distances, which I had a little divide sign, square that answer, and then if they get farther apart in the problem, we divide it into the original force, and if they get closer together in the problem, we multiply it by the original force. All right, so pause me if you need to get that. I'm going to skip number 2 and go to number 3, just because now we have a situation where we're getting closer. So if the gravitational force between 2 objects that are, here we go, 20 meters apart, it's 100 newtons. 5 meters apart. We're looking for how strong would it be if they get closer. 3 steps. Compare your distances. 20 meters divided by 5 meters gives us a 4. Second step, square it. 4 squared, 16. Third step, decide. Are we getting closer together or farther apart? We started at 20, we ended at 5. Our original force is 100 again, but this time since we got closer, we multiply. So 100 then multiplied by this 16 means we now have 1,600 newtons of force between these objects. 1,600. Just going to do one more, and then there should be an answer key for the other two on Moodle. So number 4. Two objects, 15 meters apart, the force is 200. Looking for the new force if they become 60 meters apart. It's very repetitive, but that's good because the process is always the same. 60 meters divided by 15 meters is 4. Second step, 4 squared, 16. Third step, I guess I should put second here. Third step, we've got our 200 newtons. This time, we went from 15 to 60 meters. If we get farther apart, we divide. Divide by 16, and that, my friends, I cannot do in my head. So 200 divided by 16. We'll round to the 10th, which means we're going to keep that 5. So the new answer is 12.5 newtons. All right, 12.5 newtons. All right, that is the content from LT2. Good luck.